Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020. And the title of this lecture is Solving Systems of Differential Equations Algebraically. And the algebraically is in quotes for reasons you'll understand. By way of introduction, simultaneous ordinary differential equations involve two or more equations that contain derivatives of two or more dependent variables, the unknown functions, and there's always with respect to a single independent variable, usually x or t. The method of systematic elimination for solving systems of differential equations with constant coefficients is based on the algebraic principle of elimination of variables. We shall see that the analog of multiplying an algebraic equation by a constant is operating on an ordinary differential equation with some combination of derivatives. Let's lead off and talk about some examples of this. When a substance decays by radioactivity, it doesn't just change in one step into a stable substance, but rather the first substance decays into another radioactive substance, when in turn decays into a third, and so on. This is called radioactive decay series, and it continues until a stable element is reached, and this is the sequence that happens for U-238 uranium, and it eventually becomes lead. And so suppose that we have a radioactive series described by this. So x is changed into y, and y is changed into z, and these are the decay constants for the substances, and that z is a stable element. And suppose that x, y, and z denote the amounts of capital X, y, and z respectively. So then here's what happens. We have dx dt is equal to minus lambda 1 x, and dy dt is equal to, now you see some of dx dt is coming in here, so this is going to be positive lambda 1 x, but then it's decaying itself, so that is minus lambda 2y, and then that decays into the stable element there, so that is dz dt. But you see you have three linear differential equations in and three unknown functions. Let's talk about an example here where we have pure water coming into a tank, and some of it is flushed into this tank, but this tank also recycles material back in there. Some brewing systems actually do this at distilleries. And then this flushes out a mixture of 3 gallons a minute. Now this is a mixture problem, but we end up talking about x1 being the amount of the substance in A, the solid. You could think about it as being salt, and x2 is going to be the amount of the substance here, and so the equation is going to say that dx d1 is going to equal, it is going to be 3 gallons a minute, that is coming in, times 0 pounds per gallon, plus this is also coming back from B, and so that is 1 gallon per minute, but it's coming back from B where it is mixed into x2 by 50, that is pounds per gallon, so that is coming back into this first tank, but then we're leaving the first tank 4 gallons per minute, and this is the mixed x1 over 50. And if you simplify all those things and leave out off the units, you get that dx1 is minus 25 over minus 2 over 25 x1 plus 1 over 50 x2. Similarly for tank B, you can go through that analysis and you get this. So you have, again, two differential equations, a system of differential equations. I talked about the predator-prey model when I was talking about using Laplace transforms for this, and I only make note that in this complicated example, it ends up being nonlinear, and generally these predator-prey modules will be nonlinear, and they are much harder to solve than what we're going to be talking about. Also, there are examples in electricity using networks, and you end up with linear equations here. Okay, now what we're going to be about is we're going to be using the familiar elimination method for solving these things. So we're going to be working to get x by itself, y by itself, and z by itself. That's called the elimination method. So here is, finally then, a problem I would like for you to give it a go. There are two equations and two unknowns. So x prime of x is equal to 3x minus 4y plus 1, and y prime is 4x minus 7y plus 10t. know what to do. And we'll find out how you do in 34.1.